And welcome to Unit 4, Lesson 2. We're going to find limits algebraically. Welcome back to a video. Hopefully you won't find this too excruciating, and many of you might find it helpful to actually print out the notes so that you have less to write. This is just going to be an introductory video. There won't be a whole lot of writing or a whole lot of examples. I'll leave that to teach in class. So what is a limit? And if we recall from our previous lesson, it's a y value. It is a y value that describes the immediate behavior on the left and the right at a certain x value. So we learned how to find limits numerically and graphically, but it might be a little bit more straight to the point if we can do them algebraically. So the first rule of finding limits algebraically is always to use direct substitution. But direct substitution only is going to work for what we describe as well-behaved functions. What do we mean by that? Let's do a couple of examples. All right, if I use direct substitution on example 1, where I want to find the limit as x approaches 1 of x squared plus 1, all I do is direct substitution. I'm going to take the 1, I'm going to substitute it in for x. That yields 1 squared plus 1, and the answer to this is 2. Now, for the skeptic in you, we can verify this analytically by also looking at this numerically and graphically. So if we look at this graphically, here is the graph of x squared plus 1. And notice how I've already plotted the point 1, 2. So the y value on the graph, because it's a continuous function, there's no gaps, there's no asymptotes, there's nothing weird. So the y value as we approach 1 from the left and from the right is 2. From a graphical perspective, I've made a spreadsheet where I've put in 0.9, 0.99, 0.999, 1, 1.001, 1.01. I've taken values really close to 1. And if we look at the behavior of 1.81, 1.98, 1.998 is headed to 2. And if we look at the behavior from the opposite end, coming in from the right, 2.21, 2.02, 2.002 is also going to 2. So if we look at this algebraically, graphically, and numerically, hopefully I've convinced you that the limit as x approaches 1 of x squared plus 1 is indeed equal to 2. So now let's talk about what our answer means and why this is considered a well-behaved function. Well, the first item is that f of c is defined. C is referring to the place in which I'm taking a limit. So in this case, it's 1. So f of 1 is defined on the graph. We saw that. Secondly, the limit exists. It's defined. The limit is 2. What makes this well-behaved is that where c, or in this case 1, is defined on the graph, it's also equal to the limit. This is what makes it well defined. Therefore, this is considered a well-behaved function. So let's look at some other functions. We're going to look at just solving these algebraically by using direct substitution. So for example 2, if I have the limit as x approaches 2 of x squared minus 4 over x minus 3, I'm just going to substitute in 2. So I get 2 squared minus 4 over 2 minus 3, and I end up with 0. And folks, 0 is still a number. So that doesn't mean that the limit doesn't exist. The limit is at 0. A y value can be 0. Let's look at example 3. I'm going to input negative 1. When I put in negative 1, I get 4 times negative 1 minus 5 over 3 minus negative 1. And when I do the computation, I end up with negative 9/4. So the limit as x approaches negative 1 of that function is negative 9/4. For example 4, my arithmetic is a little trickier. I have to input a fraction. Don't let that throw you off. It's still direct substitution with some messy fraction, complex fraction work. So notice here I put in negative 3/2 in for x. The numerator simplifies to negative 1/2. The denominator, when I square negative 3/2, I get negative 9/4. 9/4 times 2 gives me 9/2. 9/2 plus 3/2 is a nice 12/2, which gives me 6. Negative 1/2 over 3 simplifies to negative 1/6. Now again, for those of you who visually need to see it, let me show you how the answers to these are true graphically. You should always look at your limits in multiple ways. You should analyze them to make sure it makes sense. For the sake of time on this video, I'm going to spare you the numeric interpretation, But let's look at example 2 where I have x squared minus 4 over x minus 3. Here's what the graph looks like, and I've put it on graph trace. If we want to know what's happening at 2, I'm just going to type in 2, and I see that at 2, that the y value or the limit is at 0. In this case, the reason this is a well-behaved limit or well-behaved function is because where 2 is defined on the graph and the limit are the same thing. So what does this mean? The limit as x approaches 2 and f of 2 are the same place on the graph or on the function. Now let's look at example 3. I have gone ahead and I have graphed 4x minus 5 over 3 minus x. And if I want to know what is happening at negative 1, then at negative 2.25, which we got as negative 9/4, is the limit. So graphically, here's what's going on, and this is well behaved because where the function is defined, so f of negative 1 is also equal to the limit. We look at example 4, where I've already graphed x plus 1 over 2x squared minus x minus 3. I'm going to use a decimal just for the sake of ease. If I want to know what is happening at negative 1.5, I get negative 1.6 repeating, which is negative 1/6. So again, this is where it is defined on the graph. It's also where the limit exists. So this is considered well-behaved, and direct substitution is a strategy we can use to evaluate this limit because the limit is equal to where that value is defined on the graph. So as you have seen, sometimes the limit of f of x as x approaches c is equal to f of c. And it's these cases that we can find the limit by direct substitution. The algebra is very easy. You plug and chug. It's like an algebra 1 concept, but knowing when you can use direct substitution and when it's appropriate may not be as clear. So I am going to kind of fly through the next slides because the following properties support the direct substitution strategies for certain well-behaved functions. So the next slides are just reiterating when I can use direct substitution. So here are some basic limits when it should seem like, duh, direct substitution is pretty easy. If b and c are real numbers and n is a positive integer, then the limit as x approaches c of b equals b. This is talking about a constant. So here is a concrete example. If I wanted to take the limit of x approaches 3 of 4, it's going to equal 4. Why is that true? Well, if I pull up and graph just the constant function 4, then as x approaches 3, that output is going to be 4. So that is why that particular basic limit holds true. The limit as x approaches c of x equals c. Well, by direct substitution, if you put in 3 for x, you output a 3. If I have the limit as x approaches c of x to the n, then let's say I want to do the limit of x squared. I pick just an arbitrary value for n of 2. So 3 squared is equal to 9. Here's some additional properties of limits. We're going to let b and c be real numbers where n is a positive integer, and we're going to let f and g be functions with the following limits, where the limit as x approaches c of some arbitrary function f is L, and the limit as x approaches c of some arbitrary function g is k. Now, I'm going to be upfront. I can usually evaluate limits without necessarily thinking about these properties. It's kind of similar to how you solve equations without necessarily telling yourself, I'm using the inverse property, or I am using the additive inverse property, etc. But to exemplify these, I'm going to give you a concrete example. So instead of using the general limit as x approaches c of f of x equals L, I'm going to tell you that the limit as x approaches 3 of this function is 5, and that the limit as x approaches 3 of g of x is equal to negative 4. I made those up just to show you the following properties are true. If we look at the scalar multiple, so if you're taking b times f of x, you're just going to take b times the limit. So if I take 8 times f of x, and I want to evaluate that limit, I can evaluate the limit at 3 of f of x to be 5, and multiply that by 8 to get 40. The sum or difference property. Again, if I want to take the limit as x approaches 3 of adding f and adding g, then all I would do is add their corresponding limits. So I would just take 5 plus negative 4, and the limit of f plus g would be 1. The same holds true for a product. If you want to multiply f and g, you would just multiply their limits together. So 5 times negative 4, that limit would be negative 20. If I'm taking a quotient of those two, then I would divide and I would get a negative 5/4. And again, that would only hold true of g of x if its limit was not equal to 0. And the power property also works. If I want to take the limit of f of x raised to the nth power, and I know that when I evaluate the limit of f of x, it's equal to 5, I can just take 5 to the second power, and that limit would be 25. In addition, the direct substitution property is valid for all polynomial and rational functions with non-zero denominators. So, if you are taking the limit of a polynomial function, direct substitution always works. Why? Because in a polynomial function, it's continuous. There are no gaps. There are no asymptotes. So the limit and where the x value is on the graph, its corresponding y value, those are always going to equal each other. An example of this is example 1. So let's go back. When I look at example 1, x squared plus 1 is a polynomial. I use direct substitution to get 2, and I can algebraically figure out or evaluate my limit. Now for rational functions, provided when you input by direct substitution that your denominator, or as I say here, q of x, is not equal to 0. That is the main crux of this. Direct substitution works on a rational function provided it does not make the denominator 0. So examples 2 through 4 are examples of this. So let's revisit. Notice on examples 2, 3, and 4, those are all rational functions. And when we input it in 2, for example 2, negative 1 for example 3, or negative 3/2 for example 4, we never got 0 as a denominator. Therefore, direct substitution was an appropriate strategy to evaluate these limits algebraically. The direct substitution property is also valid for functions involving a radical and for composite functions. You just need to be careful when you have functions involving a radical that the number that you're inputting is within the domain of the radical function. So when you see that the following limit is valid for all c if n is odd, you can put in any number and you can take a cube root or a 5th root or a 7th root or a 9th root of any number because the domain is all real numbers. But it's only valid when c is greater than 0 if you have an even index, because we can only take the square root, the 4th root, the 6th root of either a 0 or a positive number. You're going to see a lot of mathematical symbolism here for the limit of a composite function. Again, I feel for your tax dollars that I should give you the math, but you can also, if you see a composite function, if you see a function within a function, direct substitution is also valid. Direct substitution is also valid for your trig functions, so I don't even know if it's necessary for you to write all of these down, but if you are taking the limit as x approaches c of the sine of x, then you just put c in for x and evaluate the sine of c. Again, the key here is that direct substitution is okay for polynomials, rationals, radicals, composites, and trig, provided that the input is in the domain of that function. So all of that work we've done over the last 3 semesters, looking at domain of all of these functions, this is where it's coming back to haunt you. Okay, we get it. We use direct substitution whenever we can to evaluate a limit algebraically. But what do we do when it doesn't work? And what are the strategies that I do then? Stay tuned. I will let you know at the next lesson. Have a good one.